You have probably been through this a lot. You open a coding question, you really try your best to solve it by yourself, you take your time, but you have no idea on how to approach it or where to start from. You give up, you read the tutorial or watch a video explanation online, and you end up like, how the heck did this guy come up with this solution? Solving coding questions like this during the interview is impossible. I could have never thought of that. You have to be a genius to come up with these ideas. It happened to me many times, and I know, it's super frustrating. After my initial failure at the Olympiad, now I really knew how I needed to approach problems. I was really taking my time and doing my best, but of course there were some problems in which I got stuck. And each time I was out of ideas, a little hint was all that I needed. Just an idea to get me unstuck and make me able to make some more progress and come closer to the solution. But unfortunately, I didn't find anything like that online. All I found was some editorials or some video solutions which spit out the algorithm out of nowhere. The solutions made sense, I understood them, but I didn't feel like I was becoming a better problem solver after going through them. It actually felt like I was reading Shakespeare. It's very beautiful, but I could have never been able to come up with something like that myself. Unless I found a way to come up with these ideas by myself, to unstuck myself whenever was necessary, all I could do was try to memorize all of them and hope that someday at some interview or at the Olympiad I'll encounter something very similar and I will be able to solve it. But I wasn't going to do that again. That was not an option. It took me nowhere in the past. I really felt the need of a crystal clear process to start from zero and start getting ideas, making progress, being able to unstuck myself each time was needed in order to be able to solve any coding question, no matter how hard it seemed to be at first. And so I got to work. I was putting even more time, more effort into solving coding questions, and for each question which I didn't know how to solve, I was reverse engineering the solutions that I found online in order to figure out what was the thinking process of that guy who came up with that solution. And after some time, I finally had the eureka moment and my bulletproof formula for solving every coding question took birth. And the results were mind-blowing. I was finally able to come up with those ideas and those solutions which seemed out of this world before. The only coding questions I wasn't really able to solve entirely by myself were those ones involving a new trick or a new algorithm which I haven't heard about. But even for those questions, I was amazed to see that I was able to come up with great ideas and at least make some progress. And now, in this video, I hope you are ready because I am proud to present to you my bulletproof formula. Buckle up. The formula consists of 3 pillars as follows. The first pillar: whenever you think of a coding question, what I want you to do first is to try to come up with a brute force approach. A brute force approach is the easiest but slowest solution that you can come up with to solve a coding question. The time this algorithm takes to execute is usually far greater than the optimal solution, and this is actually why a lot of students underestimate their power. They think like this: okay, this coding question probably has a solution in big O of n time, performing at most 1 million iterations. So why would I waste time thinking about a stupid slow solution in big O of n cube, which not even a quantic computer would be able to solve it in time? Well, first of all, a slow solution is better than no solution at all. And I actually have a funny story about this. I have a friend which had a coding interview at some normal company in Romania, and he was able to pass that interview even though he couldn't find the optimal solution to one of the problems. He was very surprised by the result himself, but he thought, okay, maybe they really loved his CV or maybe they really liked him during the interview. But that was not the case. A couple of months later, he befriended the interviewer and he asked him why did he pass. The interviewer told him that actually no candidate was able to find the optimal solution to that problem, but he was the only one who at least came up with a brute force approach, was able to explain it well, and was able to code it well. I think that speaks for itself. Second of all, nobody tells you this, but a lot of times the brute force approach is very close to the optimal one. You just need to come up with it, and then find its bottleneck, the part of that algorithm which can be optimized, and there you have the optimal solution. And even better, those optimizations are not hard to find at all. They are usually done using a data structure or a technique which you've learned in the past and was designed to solve exactly that job. But how do we come up with brute force approaches, you might ask? Well, it's actually super straightforward. Each coding question gives you some input and expects you to return some output, some solution. What a brute force approach usually does is that it tries each and every possible candidate to that solution until it finds the correct one and returns it. And I'm going to give you an example of a classic problem in which the brute force approach is super straightforward and then the optimization is super simple. That problem is called toSum. You are basically given an array of integers and another integer s, and you should find a pair of integers from that array which add up to s. How do we come up with a brute force approach? Well, what is the solution? A pair of integers from the array. So we should try out each and every possible pair of integers from the array. How do we do this? Well, there's no problem if you have no idea, we'll get there, but for those of you a little bit more experienced, you know that this can be achieved using two nested for loops. We try out each possible pair of integers, then we write an if statement checking if their sum is s, and if so, we return the elements. And we have a simple, slow brute force approach. What's the optimization? Well, we probably only need one for loop, so we can try out only one element from that pair. Let's say we fix the first element, and then we need to find if there is a good corresponding second element. And we know what its value should be. So we need to look for a specific value in a set of values. And for those of you who know, there is a simple data structure which does this for us. Okay, no more technical stuff for now, but this was just a simple example to show you how in order to optimally solve a question, it is actually best to start with that brute force approach, that stupid slow approach, and then how the optimization needed is actually super straightforward because it is basically the definition of a data structure which you know. There is a little caveat. Of course, not every coding question has a simple, intuitive brute force approach like this, or even if it has, the optimal solution might be completely different from that. But that's no problem, trust me, the next two pillars of the Bulletproof formula will help you solve those more advanced questions by yourself. The second pillar of the Bulletproof formula. Whenever you get stuck or you have no idea on how to approach a coding question, you should think of an easier version of that question. There is no magic formula, unfortunately, on how to make a problem easier, but usually you will take a property or a constraint from that problem and reduce it. And let me give you an example of such problem. Let's say you are given a basket full of fruits, and also in front of you, you have a table. At each step, you should take one fruit out of the basket and put it on the table. You are going to put the fruits in line, one after another, and your goal is to have the basket empty, so take each and every fruit from the basket, put it on the table, such that in that line, each two adjacent fruits are distinct. This problem is not easy at all, because you have a lot of options at each step, and you cannot change your mind. What should be the first fruit that you place on the table? You have to make sure that you make an optimal decision, such that with all the fruits remaining in the basket, you can arrange them on the table respecting the property. Then what should be the second fruit? What about the third? And so on and so forth. This question can be made way much easier by reducing the different number of types of fruits you start with in the basket. Think about it. In the world, there are maybe hundreds of different types of fruits. Thinking about that problem is super complex. But what if you only have one different type of fruit? What if you only have apples in the basket? Well, that's much easier, right? You have to take an apple, put it in line, and then if you have another apple left, there is no solution because you will have two adjacent apples. Now we know how to solve this question for one type of fruit. That is awesome. If you don't know how to solve it for one type, how can we be able to solve it for hundreds of types? But that is still not very helpful. This problem is actually too easy and it doesn't help us solve the original one. So what we should do now? Increase the difficulty of the problem a little bit. Increase that constraint, that property, step by step. So now we are going to think about the problem for two different types of fruits. Let's say in the basket there are only apples and bananas. Is it much easier than the original problem? Yes, it is. Because for the first fruit, we only have two options. Option number one, we choose an apple and put it first on the table. Now, what should be the second fruit? Well, obviously, shouldn't be another apple. So we have to take out a banana and put it on the table. What should be the next fruit? Obviously, not another banana. We take another apple, put it on the table. Then we take another banana, put it on the table. And so on and so forth, until we either finish all the fruits in the basket, which means we have a correct solution, or until we need the next fruit, but we don't have it in the basket, which means that this is not a valid solution and we shouldn't start with an apple in the first place. Now, the second option, we can start with a banana. Put a banana. What should be the next fruit? Not another banana, obviously. We take an apple, we put the apple. The next fruit, not another apple. We take a banana, put the banana, and so on and so forth until the basket is empty or we need the next fruit but we don't have in the basket, which means there is no solution starting with a banana. Now we know how to solve this question for two different types of fruits. Is it enough? Well, not really. Do we have a solution for the general problem? Not yet. What should we do next? Increase the difficulty a little. Think about the problem with three different types of fruits: bananas, oranges, and strawberries, let's say. And after you came up with the solution for three different types of fruits, you will see that that exact solution is the same for any number of different types of fruits. And the third pillar of the formula is to take a lot of small examples and solve them on paper. There is no theory for this, I think it is pretty explanatory, but one more important thing that I want to mention is that we will often combine two or maybe all of the three pillars in order to solve a coding question. For example, in the previous problem with the fruits, I love it so much because when I first tried to solve it, I had no clue about how to do it. I read the solution and I was like, wow, this is such an awesome solution, but I could have never been able to come up with it myself. And what's amazing about this is that after I developed the formula, 2 years later, when I thought about the problem, I was able to come up with the solution in under 10 minutes. How did I do it? I combined the second and the third pillars. I first thought about one different type of fruit, that was easy. Two different types of fruits, that was easy. But for three different types of fruits, I actually got stuck. And then I told myself, why don't I use the third pillar? Why am I even thinking about this easier version of the problem, but with n fruits in the basket? When I don't know if I'm able to solve it for 3 fruits, then 4 fruits, 5 fruits, and so on. And so I did. I started with 1 orange, 1 banana, 1 strawberry. And I saw on paper that every arrangement is a valid one. Okay, not very helpful. Then I took a little larger example on paper. Let's say I have 2 bananas, 1 orange and 1 strawberry. Now I can see that not all the arrangements are valid, but only those which start with a banana. So maybe it is optimal to always start with the fruit that occurs the most number of times. I've written this observation on paper and then I moved on and tested it. I took more and more examples. Then I took a little larger examples. Let's say I have 3 bananas, 1 strawberry, 1 orange. Okay, it still works. And I continued. After solving a couple of more small examples on paper, I was able to come up with the final observation. I tested it, and then I proved that that approach actually works for any number of fruits in the basket and for any number of different types of fruits. And the problem was solved. And this is it, guys. This is my bulletproof formula for solving every coding question out there. Let's wrap it up real quick. Pillar number 1. I always want you to start by thinking about a brute force approach. As I told you, a slow approach is always better than no approach and is much closer to the optimal one than you actually think. The second pillar, I always want you to think of an easier version of the problem. And again, there is no magic formula for this. You won't get it from the first time, but you will see that with experience, and as you will see me use this pillar for many coding questions, you are going to get it. And the third pillar, which you should always use, but especially in combination with the first two ones, is that I want you to take a lot of small examples and solve them on paper. Those small examples will help you make some awesome observations, which you will then test on more examples. You will then make those examples a little larger, make some new observations until you get to the final solution. I hope you enjoyed it, and I can't wait to see how this formula will make you an amazing problem solver.